Hi everyone, welcome back to an exciting session in Computer Vision Talks. The title for today's talk is Conformal Inference of Counterfactuals and Individual Treatment Effects. Today we have with us Dr. Lihua Lei, who is currently a postdoctoral researcher at Stanford University, mentored by Professor Emmanuel Candes. He completed his Ph.D. in statistics from UC Berkley, advised by Professor Peter Beckel and Professor Michael Jordan. He published around 23 publications in top conferences and journals like ICML, NeurIPS, ICLR, AISTAT, etc. His research interests include conformal inference, causal inference, multiple hypothesis testing, network clustering, high dimensional statistical inference, optimization, and econometrics. We are excited to have Dr. Lee with us today. Over to you, Dr. Lee.
Thank you for the introduction. So I'm going to share my screen. Okay. So thanks for having me, and I'm very happy to share my recent work on conformal inference of counterfactuals and individual treatment effects. And this is a joint work with my postdoc advisor, Emmanuel Candes. So before moving on, because this is a talk on causality, and we know that there are multiple frameworks to do causal inference. And here in this talk, I will focus on the potential outcome framework. Although our method can also be applied to many other frameworks. And just to make sure that everybody is on the same page, I will give you a brief primer on potential outcomes. So let's say, suppose we have two guinea pigs, and they're identical, but they live in two parallel universes. And in one of them, in one of them, we apply the treatment. And after that, we observe the outcomes. So in this case, when we apply the treatment, we see that the guinea pig survived, and otherwise the guinea pig died. So these two outcomes are what we call potential outcomes. And in reality, we can only observe one of them based on whether this guinea pig is receiving the treatment or not. So in words, a potential outcome is what would have been one's response had one taken the treatment. And this was first introduced by Jerzy Neyman in 1920s, and then further developed by Leon Rubin in 1970s. And there's a crucial concept called sign stable. So let's suppose 10 units, and five of them are in the treaty group, and the remaining 5 are in the control group. Then we can observe all of their covariates, X, and we can observe all their treatment assignments, T. But then for the treaty group, we can only observe their Y1 because they're treated, while their Y0 are missing. And similarly, for the control units, we can only observe their Y0 while their Y1 are missing. And sometimes when you write this down, you implicitly assume that the observed outcome only depends on your own treatment assignment. And this is sometimes called a pseudo assumption in the literature. So in this talk, I will focus on this potential outcome framework just for simplicity. And in particular, I will use T to denote a binary treatment, and use Y1 and Y0 to denote the pair of potential outcomes, and use X to denote the set of covariates. And here the covariates can be continuous or discrete or anything. And throughout the talk, I will make the following 3 assumptions: the IID assumption, and also the pseudo, which I just mentioned. And finally, there's a crucial one, which is the unconfoundedness assumption, which assume away any confounder that affect both the potential outcomes and the treatment assignment. So put it another way, this assumption states that given any value of the covariate, we have a completely randomized experiment. So the treatment assignments is completely independent of the potential outcomes. So the goal of this talk is to find an interval estimate C hat as a function of the covariate, such that it covers the individual treatment effect with probability 90%. And here, the individual treatment effect is defined as Y1 minus Y0, which is a random variable in principle. So given this goal, we can at least have 2 tasks. First, if we want to achieve this goal for subjects in the study, then we know that only one of her potential outcome is missing. So in this case, we will show you that this reduced to the counterfactual inference, meaning that we only need to make inference on one of the on the missing counterfactual. But of course, if the subject is not in the study, both of her potential outcomes are missing, and then this reduced to the pure ITE inference. And in this talk, I will focus on the first one. So before moving on to our method, I will briefly discuss the relationship between ITE and another thing which is very popular in the heterogeneous treatment effect literature, which is called conditional average treatment effect, or CATE for short. So the definition of CATE is the conditional expectation of ITE. And from the formula, you can tell that unless ITE is a deterministic function of X, CATE is not equal to ITE. And so CATE has been widely studied in the literature, and there has been a lot of recent progress on estimating CATE, and they're all very good. But we know that in statistics, nothing is perfect. So here I want to point out two limitations, which may be amplified in high-stake decision-making. And the first one is, because CATE is a conditional expectation, so it's an average over some groups defined by the covariate values. So by definition, the expectation will ignore the uncertainty around the CATE function. Just to illustrate, suppose we have age, gender, height, and smoking. We have these variables. And then we could still have three scenarios, all with CATE equals to 1. But in the first one, everybody got the positive treatment effect, while in the last one, only 20% of them get the treatment effect. But in this case, if we were in the first scenario, then we should definitely recommend this treatment. If we are in the third one, we may not want to recommend it. So this means if we're using a conditional expectation as demand, then we could potentially miss an important source of variability, which may affect our decision. So that's the first limitation. And the second limitation, again, is about uncertainty, but this time it's about uncertainty of the CATE estimator due to finite samples. So we know that this is a function, and we estimate it. And so estimating a function or getting the uncertainty correct for a function is challenging. And here I'm going to show you a very simple simulation setting, which I will give you more details in the end of the talk. And here, roughly speaking, this simulation setting is very simple in the sense that the data generation process is very sparse and very smooth. So the point of this simulation is to show that it's to give you a very simple data generation process on which every method should work well. Otherwise, it's hard to convince other people that this method should be used in more realistic applications. And here I consider three existing popular methods: the causal forest, the X-learner, and BART, where these two are frequentist methods, and BART is a Bayesian method. It's Bayesian additive regression tree. So all of these methods are very good in terms of the mean square error or the accuracy of the point estimate of CATE. So these three methods have been widely used in practice. But here I'm not going to show the accuracy. Instead, I'm going to show the coverage of the three methods, where the target is CATE. And here, for both settings, where in left panel, we only have 10 covariates, which is a very low dimensional case. While in the right panel, we have 100 covariates, which is still not very high dimensional. And in both settings, we set target level at 95%. But you see that when I apply the three methods, they all undercover, meaning that they're all overconfident about their prediction. And turns out in this case, the coverage can be as low as 75% or even 50%. And this overconfidence may not be a big issue for some low stakes decision making. But if it is something about lives or some other high stake decisions, then this could be very devastating. So sometimes I think, especially in those sensitive environments, we want to get rid of overconfidence. So we can afford to be underconfident, but we don't want overconfident. So lastly, I will make this quote from Dr. Julie Pearl, who make a clear distinction between the CATE and IT. And his point is that if we want to interpret something as an individualized effect, we need to use this IT rather than CATE. So that's pretty much about background. Is there any question? So I did see something came out in chat, but it's a little bit hard for me to monitor that.
Yeah, Lihua, no questions as such.
Yeah, okay.
It was just a message on the group to post the questions if any. So we would be monitoring the chat and we'll let you know if anything pops up.
Okay, yeah, thanks. Okay, so I will go ahead. So now let's talk about counterfactual inference. So suppose we have a testing control unit. And by definition, we know that her y0 is observed while her y1 is missing. So in this case, suppose we can find a C1 hat, an interval estimate that covers y1 with probability 90%, given that this person is in the control group. Then we can contrast C1 hat and y0 to get an interval for IT. So a simple algebra will show that this IT interval will cover the IT with probability 90%. And similarly, we can imagine that we have a treaty unit, and then if we can get a valid interval estimate of y0, then we can contrast the observed outcome y1 with this C0 hat to get an interval for IT. And so if we take this IT interval as the one we produce, then we know that it has valid coverage given within either the control group or the treaty group. And so unconditionally, it will satisfy our coverage criterion. So these two lines show that we can reduce our tasks into finding a C1 hat that covers y1 with probability 90%. So in other words, we turn our problem into a counterfactual inference problem. And now let me briefly review this data generating process. So first, there's a concept called propensity score, which is defined as the probability of being treated given the covariate value. And then for each person here, we would have this score. And for each person here, we will toss a coin and to see whether it's head or tail. And based on that, we assign this person into treaty and control group. So here in this case, we have 5 treaty and 5 control. And by Sutva, we know that we can observe y1 for this treaty group and y0 for this group, for the control group, but 0 for the treaty group, y1 for the control group. So now our goal is to make inference of y1 of a control unit. And a naive is to use this observed treaty group to make inference on this unit, because this group is the one that carries the information of y1. But there's a problem, which is that there's a distribution mismatch between these two populations, between the study population and target population. So it turns out that the joint distribution of x and y1 can be decomposed in this way for the observed treaty group, where the conditional distribution of y1 given x is this, and the covariate distribution is x given t equals to 1. So this is by definition, because this is the treaty group. Well, for this pink group, we know that the conditional distribution is still the same, but the covariate distribution is different. It's x given t equals to 0, because this is from the control group. So in sum, here we have a distribution mismatch, and in particular, we have a covariate shift. And here is the illustration of what's happening. So in the left column, I plot the real world observations, while in the right column, I plot the counterfactual observations. And in the top row, I make the scatter plot of y1 versus x. So now you see these two scatter plots look very different. But what we know is, given each slice of x, the distribution of y1 is the same. And the difference is purely driven by the covariate distribution, the difference of the covariate distributions. So having said all of this, we reduce our goal into the following. So we're going to use IID samples from one distribution to construct a predictive interval of y1 with correct coverage under another distribution, which has a covariate shift. And using the Bayes formula, we can show that the covariate shift is proportional to 1 minus propensity score divided by the propensity score. So here, the exact formula here is not very important. The crucial thing is this covariate shift is purely driven by the propensity score, or purely driven by the selection. And that's pretty much about the causal part of this talk. And now let's move on to the actual meat of this talk, which is the conformal inference, which is the real thing that combines machine learning with causal inference. So conformal inference was first proposed by Vladimir Vovk in 1990s, and it was further developed by his colleagues. And recently, it was getting a lot of attention in machine learning and statistics communities. So roughly speaking, this method will take IID samples as input, and then it will wrap around any black box predictive algorithm and turn that point prediction into a set prediction with the correct coverage. And turns out, it has a magical theoretical guarantee that this coverage holds infinite samples without any distribution on the joint distribution of x and y, and without any assumption on which algorithm you're using. So you can use linear regression, you can use neural net, anything is okay. You always get this guarantee. And of course, although this is like a magic, but we cannot directly apply it because we have a covariate shift. Unfortunately, 2 years ago, there was a paper which extends this conformal inference to the case of covariate shift. And this paper called it weighted conformal inference. And as with the standard conformal inference, this framework takes IID inputs, and then it wraps around any predictive algorithm and turn that point prediction into a set prediction with the same guarantee, as long as the covariate shift.
Hi, Dr. Lee.
Yeah.
So when we refer to covariance shift, does that mean with respect to test data?
Yes, exactly. Yeah. So you see that here, usually when we say covariate shift it's like the covariate shift between testing and training data. But here in our case, you can view this observed treaty group as the training data, and you can view this hidden counterfactual as the testing data. And that's the same covariate shift that people often talk about. Yeah.
Yeah, thank you.
Yeah, great question. Yeah, so here you see that this framework is able to take the covariate shift into consideration. And in this talk, I'm going to illustrate one instantiation of this framework, which is the weighted split conformalized quantile regression. And now I'm going to illustrate this. So this method will start by randomly splitting the data into two folds, a proper training set and a calibration set. And then on the training set, we apply any quantile regression method. It can be linear quantile regression, or a quantile random forest, or a quantile boosting, or even quantile neural net. Anything is okay. Then we're applying these techniques to fit the 5 and 95th conditional percentiles of y1 given x on this training fold. And then this will give us two curves or two functions. And then I will apply these two functions on the calibration set. Okay. And once we do this, then we calculate something called the sign distance of each point in this calibration set. So the sign distance is the distance of each point to the nearest quantiles multiplied by a +1 if it is out of the range, or -1 if it is inside the range. So the formula for that is that this is the maximum of two things. But I think intuitively, it's just a sign. It's just sign distance. So let's say, suppose we have 300 points in this calibration set. Then we will have 300 sign distances. And we can collect all of them. And this histogram is just a histogram. So the usual standard inference directly on shift, we will reweight this histogram based on the covariate shift. So you see that here there's a mathematical formula, but you don't need to parse it because the only message here is that we are going to reweight this gray histogram, and the weight is computable as long as the covariate shift is null. And roughly speaking, it's proportional to the covariate shift. So if the covariate shift is unknown, then we can estimate it and plug in. So once we have this blue histogram, then we can take the 90th percentile of this blue histogram and call that QX. And finally, we will output these two black curves plus and minus QX. So in other words, once you see this, you may see that this QX is a calibration term. So suppose we can get the conditional percentile correct, meaning that this Q hat 0.05 and Q hat 0.95 are close to the true conditional percentiles. Then we don't need to do any calibration, because in this case, by definition, for any x, the coverage of this interval is 90%, which is 95 minus 5. But the modern machine learning algorithms tend to be very complicated, and in many settings, we have seen that they are overconfident, meaning that they overestimate the 5th percentile and underestimate the 95th percentile. So in this case, if we simply use this crude interval without this calibration term, we will be overconfident. But in this case, this calibration term will be positive, meaning that we will save ourselves from being overconfident. And that's how this method works. So you see that the whole procedure is very simple. It's wrapped around an estimate of these two conditional quantiles and then recalibrate them. And the calibration process is very simple. It's just based on 300 calibration points. Or, I mean, the 300 is not essential, but it's just the size of the calibration set. Okay, so that's about our procedure. And similar to the standard conformal inference, we would have a strong theoretical guarantee on this procedure. So the first one is about randomized experiment, in which case we know the propensity score exactly. And in this case, we can use that propensity score in our procedure. Then what we can get have two parts. The first is that we can guarantee this coverage to be above 90% without any extra assumptions. And this means this holds for any conditional distribution of y1 given x. It holds for any sample size, and it holds for any procedure to fit conditional quantiles. And you see here, as long as we can give it the correct propensity score and our estimator Q hat, then this procedure will wrap around this black box to produce a trustable interval estimate. So that's the first result. But of course, just getting this lower bound is insufficient. because we don't want to be too conservative. So because if you just want to achieve this criterion, you can set C1 hat to be minus infinity to infinity, which will give you 100% coverage. But that's definitely not what we want. So it turns out under two other admired conditions, like the first one is if the sign distance are almost surely distinct. So this will be true if either your y or any of your x is continuous, then this will be true. So this is pretty mild. And second, we need some overlap condition, or we need some control on the propensity score to avoid that this is too small or too large. Then we could have an upper bound as 90% plus some universal constant times n to the minus half. So in other words, as long as n is reasonably large, this guarantee will be very tight. So later on in the simulation result, I will show you how tight it is. So it's not just a theoretical result. It's something that you can see, you can observe from the real examples. So to summarize here, for randomized experiment, if we know the propensity score, then we can achieve near exact coverage, which is 90%. But of course, in general, for general observational studies, or if you have a randomized experiment with some compliance, non-compliance, then the propensity score has to be estimated. So in this case, we can plug in an estimated version of the propensity score. And informally, we can show that this coverage is approximately 90% if either the propensity score is well estimated or the conditional quantile are well estimated. So here I highlight this or here, meaning that I only need one of these two assumptions to be true. So in other words, if we can get propensity score correct, then we can afford arbitrarily bad conditional quantile estimate. And meanwhile, if we can get the conditional quantiles well, then we can afford arbitrarily bad propensity score. And this is similar to the double robustness for average treatment effect in the classical causal inference literature. And moreover, if the conditional quantiles are estimated well, as I mentioned before, in this case, the calibration term is approximately 0, because here we don't need calibration. So it turns out, in this case, we can achieve an even stronger guarantee that the coverage, the conditional coverage, is approximately 90%. So in other words, if we can get our model correct, then we can achieve a stronger guarantee. So that's like a no free lunch theorem. So it's like, if we can know the propensity score, we know that this guarantee always holds, even if our model is misspecified or our model fitting is bad. But it doesn't mean that we should use a bad model, because this results show that if we are using a good model, we can achieve a stronger guarantee. So that's like the trade-off between validity and power. Okay, so that's pretty much about the theoretical guarantee. Yeah, please.
Yeah, if we consider X as image, so what is C1 hat of X in this case?
Yeah, so C1 hat is still this. But you see that when you calculate this calibration term, you need this blue histogram, and then you need this weight. So in this case, this covariate shift is not fully known. And here we plug in the estimate. So we plug in W hat here to get this weight. And in particular, W hat is 1 minus E hat divided by E hat. So this C1 hat. Sorry, go ahead.
How will C1 hat look like in case of images?
So this C1 hat is just two numbers. So let me go back. Yeah, so you see that this C1 hat is an interval. So it has two numbers. One is the lower bound, the other is upper bound. But these two numbers depends on the covariate value. So for different covariates, you may have different two numbers. Does that address your question?
I'm getting that we are using the sign distance to bound this region with the C hat of S.
Yeah. Yes, it's still the same. So the case for this observational study is the same for the one I just illustrated. So here you see, once you get the calibration set, you so this estimate are still from the training set, the conditional quantile estimate, and then on the calibration set you calculate the sign distance, and everything is the same. So the only part where the estimated propensity score kick in is on this rebaiting scheme. So before that, there's nothing about the propensity score estimate. Yeah. So that's a great question. So you see that the conditional quantile estimate, got in this sign distance calculation, while the propensity score estimate is in the rebaiting scheme. Yeah, they have different roles. Okay, yeah. So that's our theoretical guarantees, and you see that it's very different from many theoretical results from theoretical machine learning or theoretical statistics, where you have a lot of asymptotic settings, where you assume something is going to infinity, and you assume that you have a correct model. So a crucial assumption is usually that you have a correct model. But here we don't need that. And our theoretical guarantee relies on very weak assumptions. And before moving on to the next part, I want to comment on this, the general counterfactual inference part, which is, so previously we consider a particular target distribution, where the covariate distribution is the covariate distribution in the control group. But in general, we can replace that by any distribution. So for example, and in our paper, we give several important examples, but one interesting one is this generalization, meaning that suppose your study population is not representative enough, and you want to generalize your results to another population. So let's say you run an experiment in California, but you want to generalize to the whole US. So then there must be some actual covariate shift. And turns out we can just refine the weight by taking to this account. So it turns out the weight has two components. One is this covariate shift between two populations, and the other is this propensity score. It's due to selection. So once you can get these two components correctly, then you can do our method, and you can achieve the same guarantee as I mentioned before. So this is something I want to highlight a bit, is that counterfactual reasoning it's now everywhere in modern science and machine learning. So it's not just in causal inference, but also in reinforcement learning, in algorithmic fairness, and in explainable learning, many other areas. So I think counterfactual reasoning is a generic way of reasoning, which can work in many cases. Okay, so that's about the first part. And now let's move to the second part, which is how we're gonna turn this counterfactual inference tool into a IT inference tool. So here I only have one slide. This is not the focus of this talk. And a very naive approach is to get, so let's say suppose you want to get a 90% interval for IT. One thing you can do is you first construct 95% intervals for Y1 and Y0 separately. And then you contrast these two intervals. And then it's very easy to show using a union bound that this is a valid interval. And this is true regardless of the correlation structure between Y1 and Y0. It always holds. So this is what we call a naive approach. And in our paper, we also propose some other approaches which can achieve this goal. But I will skip that because that's a little bit delicate. So the punchline is that once you get a valid counterfactual inference tool, then you can easily turn that into a IT inference tool. Okay, so now let's get into the empirical results, which you may find surprising. So let's go slow here. And so this simulation is a variant of the example from the causal force paper. And in this case, we generate the covariate as multivariate Gaussian with either independent or correlated features, and with dimension either 10 or 100. And for simplicity, we set y0 to be 0, in which case the IT inference reduced to counterfactual inference, because we no longer need to make inference on y0. And we also generate y1 as a conditional Gaussian variable, with the main function depending on x1 and x2 smoothly. And also the standard deviation can be either homoscedastic or heteroscedastic. In the heteroscedastic case, it's a very simple function, simple function. And this is a very sparse function. And finally, we generate the propensity score to be bounded away from 0 and 1, meaning that we have sufficient overlap between the treated and control group. And also, this is a first function only depends on x1 in a smooth way. So here you may say simplified simulation. And that's exactly our point, because here we want to use a very simple data generating process to show that some existing method may fail to work in this case. So that's perhaps the most surprising part. And actually, this is the same simulation setting as I showed you at the beginning of the talk. So the first plot, so before that, we have an R package called CF causal. So if you are interested in this method, you can download that from my GitHub. And we have a very detailed tutorial on how to use it. So like in our package, we have some built-in learners for the conditional quantiles, including quantile random forest, quantile boosting, and quantile from some Bayesian methods. But if you want to use your own favorite method to estimate these quantiles, we also have a generic interface that you only need to write a snippet of the code, and then you can apply that into our package and run it. Okay, so that's about the software. And the first plot I'm going to show you is the marginal coverage of CATE, which is a sanity check. So the reason I call it a sanity check is because our method is not designed to cover CATE, but rather is to cover IT. So in this case, we shouldn't expect our method to cover CATE, but other methods are designed to cover CATE. That's why I'm showing this figure to show that, to show some sanity checks. So here we consider 6 methods, and 3 of them in the bottom are the ones I introduced at the beginning. So they are BART, they are XLearner, and causal forest. So BART is a Bayesian method, and these 2 are frequentist methods. And all the 3 methods are designed to cover CATE, produce intervals to cover CATE. And for our method, we choose 3 learners. One is BART, the other is quantile boosting, and the third is the quantile random forest. So the last 2 ones can give you estimate of the 5 and 95th percentile. But the first one can also do that, because the first one is a Bayesian method. So we know when we run a Bayesian method, it will give us a lot of posterior draws. So from that, we can estimate the posterior percentiles. And we just use the 5 and 95 posterior percentiles as the estimate. So you can see that for all our methods in all the scenarios. So by the way, I forgot to mention that each panel here corresponds to a scenario, where here is homoscedastic error plus independent features. And this is heteroscedastic errors plus correlative features. And the top row has 10 covariate, and second row has 100 covariate. And the sample size here is 1,000. So it's not crazy, but it's a very reasonable application. And so in all these settings, we will find that our method would have conservative coverage, which is not ideal, because ideally we want the coverage to be exactly 95%. So we don't want to be conservative. But when we cannot achieve it, it's better to be conservative than to be anti-conservative. And so that's about our method. And for external and causal forest, as I showed you at the beginning, you see that in all scenarios, they undercover. And sometimes the coverage can be as low as 25%. And for BART, we see that in homoscedastic settings, the coverage is conservative. It's above 95%. But in heteroscedastic case, they still undercover. So again, I want to echo my point at the beginning of the talk is that the coverage is a very sensitive measure. So when you set the target to be 95%, it's okay if you get 93% or 92%, but it's not okay to get 90% because that's a clear evidence of overconfidence. And let alone here, you got 75% or even lower. So this sanity check shows us that even if all these methods have guarantees, have sort of theoretical guarantees under some asymptotic assumptions, they fail to work, even in this simple data journeying process. So that's the first plot. And the second one is our actual meet, which is the marginal coverage of ITE. So here you see that in all scenarios, our method has approximately exact coverage. You see that they're fairly concentrating around this target line. So this is predicted by our theorem, which says that we not only achieve this conservative coverage, but we also achieve this near exact ones, regardless of whether you have homoscedastic error or heteroscedastic errors, where you have independent or correlative features. Nothing matters here. And for external and causal forest, you see that they significantly undercover. But that's not a reason to criticize this two method because they're not designed to cover ITE. So it's okay that they undercover. So the only takeaway from this is that if somebody is going to use causal forest and external to make inference on the individualized strip effect, then the interpretation can be subtle. So we need to be clear what they are estimating. But for BART, because BART is a Bayesian method, so although it's designed for covering CATE, but if we change the credible interval into a predictive interval, we're supposed to getting correct coverage on ITE. So it turns out for the static situations, BART does achieve a near exact coverage, and it's even better than our method. But in heteroscedastic case, BART failed to cover. So the coverage is as low as 80% or even lower. So that's about the marginal coverage of ITE. But of course, the coverage is just a type 1 error, and we want to show how tight the interval are. So that's the next plot. So in this plot, for every scenario, we have this blue line, which gives the average length of the oracle intervals. Here, the oracle intervals are formed by the true 5 and 95 quantile of y1 given x. So we know that no method can beat this oracle interval. And you see that for our method, because our method is valid in all scenarios, so you see that their average lengths are slightly above this oracle length. But you see that the gap is not too large, even with 1,000 samples here. And in particular, if you still recall that BART is doing a good job in homoscedastic cases. So in this case, you also achieve the near oracle average length, which is great, like this and this. But you see, if we wrap around BART, our average length is also close to the oracle. It's just slightly larger than the intervals produced by BART, meaning that if we're wrapping around a good model, then the actual price is very low. This echoes our theoretical result, saying that if we can get this conditional quantiles well, then we can we can achieve a stronger guarantee. We lose nothing. But in the heteroscedastic settings, we know that BART failed to cover. And in this case, our method, the average length of our method, becomes much more variable. And I think this is a very good thing because somehow our method detects that BART is not doing a good job. And then it has to compensate for this. That makes the intervals much more variable. And on the other hand, if we wrap around other methods like quantile boosting or random forest, which are more robust to heteroscedasticity, then we see that the interval lengths are quite stable and they're also close to the oracles. So finally, we see that the X-linear and causal forests both have very short intervals, but that's not a good thing because that's just because they're undercover. So it's not comparable to valid methods. So the final plot I'm going to show you is about the conditional coverage. So we know that our guarantee is mostly about marginal coverage, and we only have the theoretical guarantee when the model is correctly specified. They could achieve this conditional coverage. But in practice, that's only a sufficient condition, but necessary. So here in this example, I'm going to show you that our method can also achieve this conditional coverage. And because we have a high dimensional covariate, so it's very hard to visualize this. And instead, I will just turn this 10 or 100 dimensional covariate into a summary statistics. And in this case, it's the conditional variance. And I choose this measure because intuitively, for points with larger conditional variance, it would be harder to cover. And this is what you can see from this bar plot, where it shows a clear monotonic decreasing trend of the conditional coverage. So if you still remember this, that on average, BART has a 80% coverage, but towards this end, only have 50% coverage, which is pretty bad. But if we wrap around BART, like in this figure, see that still we didn't completely alleviate, we didn't completely solve this issue, but we alleviate this a lot. So you see that towards the end, this coverage is as high as 80%. And of course, this is still not ideal. But if we are wrapping around some stable method like boosting or random forest, we see that we see a pretty flat patterns of this conditional coverage. And that means in this case, we can control conditional coverage. And that's a much stronger guarantee than marginal coverage. So that's pretty much about the empirical results and our main result in this talk. So let me wrap up. So in this talk, we proposed a conformal inference-based method of counterfactuals and individual treatment effects, which is reliable in the sense that for randomized experiments, we can achieve near exact coverage in finite samples with any black box algorithms. And more generally, for observational studies where the propensity score is unknown, we can achieve a doubly robust guarantee of coverage. And finally, if you're interested in conformal inference in general, you can check out the tutorial on conformal inference by my postdoc advisor, Emmanuel Candes, at this Bernoulli IMS One Word Symposium. And also, because I know this is a computer vision series, so conformal inference has a lot of applications in computer vision. And recently, we got a new paper with Stephen Bates, Anastasios Angelopoulos, Jitendra Malik, and Mike Jordan. And we apply this idea to construct risk controlling prediction set in many applications in computer vision. And so if you're interested, you can also check out that paper. And with that, thank you all for your attention.
Hello, Dr. Lee.
Hi.
So there has been increased use of counterfactual explanations in explainable machine learning. So have you seen any applications of this conformal inference in explainability as well?
Not yet. Yeah, but I think you'll be. Yeah, because in the explanatory explainable machine learning, we know that we want to say what would have been the response had the input changed. So there, because we are having a black box model, so we have it will be much cheaper to collect more data, right? So it's very different from the causal inference setting where the data collection is very expensive. So because of the cheap data collection, we can have a huge sample size. And there we can get our uncertainty band very narrow. So if you're applying this conformal inference. So I think, yeah, there will be a lot of applications in the interpretability of machine learning algorithms.
Any other questions from the audience?
So like if we are done with the formal questions, more recently we've been getting requests on talking about the story of the paper. So Lihua, would you like to tell us more about how did you end up choosing this area as a field of study, and how long did you take to finish this paper, and more insights on it, like reviewers, and how was the journey overall?
I see. Yeah. So I think I got into this problem because I was working on causal inference before, and I was extremely interested in the inference part using machine learning because I had quite a few projects which leveraged the predictive power of machine learning algorithms, but trying to add a protection layer to make sure that we're not getting wrong. We know that machine learning algorithm is very flexible, it's very good for many tasks, but sometimes it tends to be overconfident. So many of my projects are about that. And then when I got into my postdoc, I met Emmanuel, and he's an expert on conformal inference. And I read a lot of his papers and also the book by Vladimir Vovk on conformal inference. And I think this is a really useful framework for many problems. So then I began to brainstorm the connection between every problem and this conformal inference. And turns out this individual treatment effect is a great application. So once we had this idea, you see that most of the part, so you see that the theorem, so they're super clean, right? So once you have a clean theorem, usually the proof is short. Otherwise, how could you get a very clean result with a very long proof? That's not easy to imagine. And so this result are not very hard to prove. And mostly we're looking for, we spend most of our times to look for interesting applications. So here I haven't shown you that, but in our paper we also have a real data analysis based on a national study of learning mindset data. And we want to demonstrate the validity or the robustness of our methods on different data sets and try to make our point solid. So most of our time are spent in, say, for example, reading the recent literature on this method and to see how they are applied and in what scenarios they would succeed and in what scenarios they would fail. So we spent a lot of time thinking about that. And the whole project took about more than half a year. I think it's around 9 or 10 months. And our paper is still under review.
Okay, great. That's great to hear. I hope you get great success with the paper. And all the GitHub idea was very clean, very organized, and it actually offers a solution and not just a theoretical proposition. So that was really great. One more thing that I would like to ask is that did you end up choosing causal inference, or your interest in causal inference develop on its own, or was it due to supervisor? Like most of the talks we host and we ask people, how did you end up coming in the domain? The answer is because their supervisor was working in that domain and that got them interested. So how was it how was it like for you?
Yeah, in my case, I think I got into this field because I was intrigued by this. Because back then, when I was a PhD student at Berkeley, there was a great causal reading group. And each semester we read one important topics. And I think I was getting interested in that. So actually my PhD advisors are not working on causal inference. And but I was intrigued by those topics and then began to work with other people on some causal inference problems. And yeah, that's my case.
That's very interesting and very different from what we have heard till now. So yeah, it would be a good idea to follow your interest and collaborate with people apart from your lab if you're really into that field, I guess. So,
yeah, in some cases, in some sense, that doesn't conflict with my work with my advisors, because somehow I think amazing part of statistics is that things are so well connected. So many causal inference problems, once you learn its language, so you can reduce that to a standard statistical problem, and that will be something else I was working on. So in some sense, I was working on causal inference, but the essence of the problems I'm working on is not too different from the other problems I was working on.
right, I get it. So in masters, you were not working in the same domain?
I didn't get a master degree, so but when I was an undergrad, I work on some other problems. I work on some econometrics problems, and then I got into PhD, and I work on quite a few areas.
I see. So from undergraduate, you shifted to a PhD.
Sorry, I shift to yes, yeah, that's right, yeah.
Right. And you were sure that you wanna do that kind of a commitment because PhD requires a lot of commitment.
Yeah, I think so yeah, it is like in the first year or the first 2 years of PhD are mostly about taking courses and starting the first 1 or 2 projects. And I think once you have done the first 2 years, then the gap was more or less filled. And then you can begin to brainstorm, or you can begin to think about which direction to go. And a good thing in statistics, I don't know if that's the case in CS, but I think statistics has a relatively slower pace than CS. So that means we have more time to do exploration. Like the exploitation trade-off for us is kind of leaning more towards the exploration part. And that means we have a chance to reach to different topics and finally decide which area to work in.
Right. That's great. That's great. So I have a few friends who got into University of California just after their undergraduate for a PhD. So most of us were like scared about the idea that what if during the PhD we realize that our interests are not now aligning with the supervisor. We want to explore another field, and we didn't have that leverage of doing a master's and checking out different fields and then choosing one for a PhD. So
Yeah.
I guess it is more specific to, yeah.
Yeah.
One last question would be, are you focused more working on the theoretical part, or do you like exploring the applications as well? Like you mentioned one application of your project in a computer vision domain.
Yeah.
In the last slide. So in statistics, do you guys focus on the applications also, or is it more focused on the theory?
We do focus on applications a lot, because in stats, I think there's no clear boundary between theory, methodology, and application. So we do want to work on theory, which can guide practice, and we do want to work on applications where things can be driven by theory. So there's no clear boundary. So I guess as in order to be a good statistician, we have to be good at both theory and applications. And application include like coding, and that's one part, but also it's about the sense of data. So once you get the data, how to make sense of it becomes a very important part, and that requires a lot of experiences and deep thinking. So I think, of course, everybody has their own focus. So some people focus are leaning towards more on theory. Some people are more applied. But I think eventually we want to be good at both.
Right. I get it. Great. It was so great hosting you. Our first talk in statistics, and this was a lot of maths. Generally, when we see a paper with maths, like a Norris paper, we want the authors to speak in detail about the maths part because that is tough. And today, this whole session was on maths. So yeah, it was great. We wish you luck for your paper. And thank you so much for coming and discussing all of this with us.
Thank you very much.
Right. Great. Nikhil, shall we end it? Any more questions? Okay. Great. Thank you.
Okay, great. Thank you. Bye-bye.
Bye.